No. Okay. So in problem number 7, we're going to rotate this blue region around the x-axis, which means that we end up getting a solid that is a cone, exactly. All right. Now, what's that line that is cyan in color? It is a representation for that arbitrary x that we've been talking about. So let's think about a cross section. The cross section, because it's from rotation, the cross section is a disk. When we grab that disk, it's grabbed in the dx orientation, and we want to find again that representation, that cross-sectional area times dx, because that's our representation of a little bit of volume. Yeah. So if we're doing things with arbitrary x, let's call this arbitrary x. And we're going to need to solve for y, indeed. So what happens when we take that linear equation and solve it for y? Looks like I get 2y is equal to 2 minus x, or y is equal to 1 minus 1/2 x. Are we good with that?
Yes.
Is there?
Yeah.
Well, actually, the easier way is not to do calculus at all.
Just plug it in the value formula.
Yeah.
That's exactly right.
That's what
So we're going to do it both ways.
Yay.
All right. So let's go ahead and say this for the arbitrary x, it's 1 minus 1/2 x. The cross-sectional area is the area of a circle, which is pi r squared. And in this case, our r is running from 0.
So it's 1 minus 1/2 x is our r.
From 0 to this, which is 1, oops, 1/2 x quantity squared dx. And if we want to finish this off, we need to add up all the little volumes from 0 to 2, because we're looking at values of x. Pull out the pi. Why don't I expand that while I'm at it? I get 1 minus 1x plus 1/4 x squared dx. Someone check my algebra. And I derivatize x minus 1/2 x squared plus 1/12 x cubed is evaluated from 0 to 2. So we're going to end up with 2 minus 4 times 1/2, which is 2, plus 1/12 times 8, minus 0, 0, 0. So we end up with 8/12 is what? 2/3. So 2 pi over 3. Now that's what they say in sorry, I called this line cyan. This line is not cyan.
Magenta.
That's magenta.
Cyan's blue.
This is cyan. All right.
Nice color lesson in our
There's no yellow on here though, so
Okay.
didn't complete that.
All right. So and using Angela's method, we know again the volume of a cone is 1/3 pi. R in this case is 1 squared times 2, so 2/3 pi. Yep. So either way, we're looking good.
Amazing.
By the way, I did it out because I wanted to just get again more practice on drawing these figures, seeing the cross section, talking about the arbitrary x. If I give you an exam in which you can use a known formula to solve it, and if I don't explicitly state you must write an integral expression, you go ahead and take advantage of your prior knowledge, okay?
Yeah.
All right. Name?
I thought you were supposed to find that volume of shaded region.
Nope. No. The shaded region is shown you so that you know what's being revolved around the axis of revolution.
So you find that stuff too.
No, it's just that area, that area is your guide to what the solid's going to look like. It's all it's doing is saying, here's how I'm going to specify that area by putting it in blue. As compared to saying, the region that is bounded by the x-axis, the y-axis, and the line. So instead of using words, they give you a picture.
I love pictures.
They're worth approximately 2 to the 10th words.
Like, why do you have to use cylinder? Like, did you have to use like cylinder?
As compared to what could else I've used?
Like pyramid. I was thinking about pyramids for some reason.
No, we call this method the disk method because we're always breaking it down. When we were talking about volumes of revolution, because we're always breaking it down to things that look like that look like really short, squat cylinders, which we call disks. Unless we put a hole in them, and then we call them washers. No, washers, not washes.
Losses.
Okay.
We just use the gentle line to save the
I feel like if you put a hole in a disc, it becomes a disc you can use.
Anybody else?
We just use the